Welcome to buffered solutions. A buffered solution, or a buffer, is a solution that resists some drastic change in pH upon the addition of small amounts of a strong acid or a strong base. So a buffer is made out of a mixture of a weak acid, we're going to call that HA, and its conjugate base A-. So remember that our weak acid HA can dissociate into protons and our conjugate base A-. And so what we're going to do is mix in some HA and some A-. Like in the last video, we had some acetic acid and some sodium acetate. That would make a buffer. So, again, our buffer contains an acidic species that will neutralize our hydroxide, and it contains a basic species which will neutralize our hydrogen ions. So, we have a mixture of our acid. If we dump in some hydroxide or some base, the acid will react with the base. But we also have a conjugate base. So if we dump in an acid, we're increasing the hydrogen ion concentration. This equilibrium shifts to the left, and we react some of that hydrogen with our conjugate base, and that doesn't eliminate, but it reduces the change in pH. So a buffer resists a change in pH. It doesn't eliminate a change in pH, but it does resist the change in pH. And over some capacity of the buffer, the pH won't change very much. Outside that capacity, then the pH will begin to change more. So when a small amount of hydroxide is added to our buffer, then the hydroxide reacts with our HA to produce A- and water. And again, remember that our acid dissociation constant for HA can be written like this. And if then the amount of hydroxide added is small compared to our HA and A-, then that A-HA ratio doesn't change very much. And this means that the hydrogen ion concentration doesn't change significantly, and neither does the pH. Because again, let's go back, if this ratio doesn't change very much, and Ka is a constant, then if this ratio isn't changing much, then the hydrogen ion concentration can't change very much. So, if a small amount of hydrogen ion is added to the buffer, then the hydrogen ion reacts with that A- to produce HA, or conjugate acid. And remember that the acid dissociation constant for HA is written like this. Same as before. If the amount of hydrogen ion added is small compared to the amounts of HA and A-, then again, that A-HA ratio isn't changing significantly. If that ratio doesn't change significantly, then our hydrogen ion concentration can't change significantly. Again, it's changing some, because that ratio is changing a little bit. But as long as we're only adding a small fraction of the hydrogen ion as our conjugate base, then that ratio won't change a whole lot. So, the pH of the buffer is related to the Ka of our acid and to the relative concentrations of our acid and base. And so we can derive an equation that shows the relationship between the conjugate acid-base concentrations and pH and Ka. So, let's do that. So remember the definition for the acid dissociation constant for Ka can be written like this. We've already seen this a few times. And we can rearrange this to solve for the hydrogen ion concentration. So let's do that. Let's put hydrogen ion concentration over there. So we get hydrogen ion concentration is equal to Ka times the ratio between HA and A- concentrations. And then if we take the negative log of each side of the equation, we have minus log base 10 of H flux concentration is equal to minus log base 10 of Ka times concentration of HA over concentration of A-. And now we can separate this term out into two different terms. We can pull out the Ka and have minus log of Ka and minus log of that ratio HA over A-. And this means that now, because this term, minus log base 10 of something, is the P of that something, we can write this term as pKa, and that term is pH. So we can say pH is then equal to pKa minus log base 10 of the acid concentration over the base concentration. And we can then rearrange that to, now note that I've swapped the acid and base, and I've then changed the sign there. So this then is the Henderson-Hasselbalch equation. So the pH is equal to pKa plus, not minus, plus log base 10 of the conjugate base concentration divided by the acid concentration. Another way of writing that is this way: pH is equal to pKa plus log of base concentration over acid concentration. Here, note that the Henderson-Hasselbalch equation is using the equilibrium concentrations of the acid and the conjugate base here, not our starting or initial concentration. So we need to know what those equilibrium concentrations are. So again, here is the Henderson-Hasselbalch equation. You should memorize that equation. That's a very important equation in chemistry and biochemistry. So if Ka is sufficiently small, which means if the equilibrium constant of HA is close to the initial concentration of HA, then we can use the initial values of the acid and base concentrations to get a reasonable estimate of our pH. So that was buffered solutions.